Okay, have you just come from the keynote? Are people still flowing in? I was wondering if I should wait or just start now, because it's, well, I guess we're 10 minutes. We're running all 10 minutes late anyway. Okay, let's just start, and if people roll in, that's good. So thanks for attending this. This is going to be something called the Invocation game, play on the movie title. We're not as smart as the person that movie's about. So I'm Paul, this is John. It really should be the resolution, linking, and invocation game, but that is not as pithy title. And this is this talk is John is going to get warmed up and get going for his next talk, where he really lets rip on the VM. So, safe harbor statement. So this is, I just want to explain what is in the current stack in JDK 8 and 9 today, and say how MethodHandles are where they are and how they're built up and what depends on what as a rough stack. So at the bottom here we have something called method signature polymorphism, which I'll explain. I call this the C of signature polymorphism. It's the C where all possible signatures can reside. And we will explain what this actually means with respect to the two things above that, MethodHandles and VarHandles. They have special methods on them. In MethodHandles, you'll see something invoke exact and invoke. And you'll see on VarHandles a bunch of methods like get, acquire, compare, and set. And they look a bit strange compared to other methods out there in terms of, if you look at the source code, the annotations they have on them, they're final, native, and so forth like this. So a method handle is essentially a dynamically typed reference to a method. That's essentially it. It looks a bit like Java lang reflect method, but it's much more powerful. I'll explain when do some coding, explain that. And VarHandles are essentially a dynamically typed reference to a variable where you can perform some exotic form of access control on there. Like we've added a bunch of new methods to do compare and exchange and so forth like that, but you can't do on the atomics we have. So the motivation for adding VarHandles to the set here was to get very fast atomic access to stuff and replace atomic field updater classes and so forth like that, and replace unsafe usage. So you can use these classes if you use them in a special way to get as fast as unsafe access that people were using to do forms of access control, like acquire release type things for lock-free algorithms. And a lot of if we move up the stack on VarHandles, some of the Java util concurrent code, like in fork join, has been modified to use VarHandles, and that is a good plus in terms of, yes, you can trust this in terms of performance, because if Doug Lee can trust this and build his fork join on there and he's okay with performance, then we're all looking good. So we need to do some more work here. One issue we have is cyclical references when we're booting up the JDK. And we need to resolve and tease apart these so I can put more stuff into Java util concurrent and replace unsafe. So not only are we suggesting others to replace unsafe when we can, we're eating our own dog food and trying to replace unsafe in our own code, because that makes it more correct and more readable and more understandable and less risk for us for crashing the VM as well. But I expect going forward, we're probably going to use unsafe in our own things for new stuff to get the performance we want too. So it's not going to be a sort of religious substitution replace with everything. So on top of method handles, we have what you might be familiar with is invoke dynamic. How many people are familiar with this concept? I see some people obviously are. So it's essentially, I call it pluggable linking. Essentially, the VM does not know how to link this call site, so it appeals to some Java code. It says, how do I link it? Here's a method handle you will call after linkage to actually invoke this call site. That's essentially it. And the method handle invocation and the VarHandle invocation of these signature polymorphic methods are actually doing a very similar trick, but it's hard-coded. Essentially, these provide hard-coded bootstrap methods, but Indy provides that generic mechanism for people outside, and us to provide a more generic pluggable mechanism. On top of invoke dynamic, we have lambdas. Lambdas, Java-C compiles lambdas, and it uses invoke dynamic to not bind to the implementation technique to how these lambdas are actually supposed out. We don't Java-C does not compile these things to anonymous inner classes. It uses an invoke dynamic with a bootstrap that generates the code dynamically. So it allows us to hide the implementation technique so we can optimize that later on. And we've done the same recently. Alexi Shipleft did string concat. You might find if you're doing A plus B plus some non-constant in there, you might find that's now encoded in an INDI as well if you look at Java P output. So we can actually optimize the concatenation of strings much better than Java-C trying to do something, and potentially hotspot too in its intrinsics in string optimization. It allows us potentially to remove a bunch of code, complex code in hotspot. Potentially, we haven't done that yet, but I think that's something we could pursue in the future and clean up that code. Then on the side, we have something called Dynalink, which I don't know a huge amount about, but I know it's used by Nashorn, and it's essentially utilities on top for building dynamic languages. That's a module in the JDK. And then we have some future stuff. I'll let John talk a little bit about that.
Okay, thank you. So we think we want to build more on top of this framework. It's been enjoyable for us, and it's allowed us to do optimizations that we wouldn't ordinarily have done before. So there's a couple things that we're thinking right now. One is that we can use method handles to call not only Java methods, but native methods. A method handle, after all, is a compiled, JITted intrinsic that has arbitrary VM assigned behavior. So why not push some raw arguments on the native stack and call a raw native entry point? Well, there are many reasons why not, right? It's not terribly safe. But when you need to do it, this is probably the most effective way to do it through a method handle as opposed to through some special API like JFFI, which always has some interpretive overhead in it. So that's like, you can take that and double down on that crazy proposition and say, well, if I'm going to call native entry points, why don't I just call native instructions? And once again, you can spin method handles around arbitrary native instructions. You give a little information to the JIT as to where the register motion is on either side of the instruction and wrap it in a method handle. And once again, if the JIT sees that in the mix of a bunch of Java code, it says, oh, okay, I guess I got to put an instruction there. I got to assign some registers and plug it in, and boom, you've got a way to directly put ASM statements in Java, which is pretty cool. When you need to do it, it's cool. When you don't need to do it, it's not cool to do it, right? And likewise with, suppose we want to introduce a new type into the JVM, value types. Well, that involves a whole set of changes through the tools, the stack, the language, the compiler, the bytecode set, the optimizations. We're not ready to do that yet, but we want to give you guys a preview of value types. So in a very soon upcoming release, we expect to be able to give you access to these new types, but not in the form of source code or bytecode, underneath the method handle. So basically say, I'm going to be able to make method handles that can work with these strange types. I just can't say them in source code. It sounds paradoxical, but it works, and we're actually able to use this technique today with some early pathfinding we're doing with Intel engineers to create, to roll the whole thing together to use value types to represent larger than 64-bit vectors and to represent intrinsics in the Intel hardware for those vectors and get tight loops out of the JIT doing vectorized code manually. It's probably the best way on earth to code with those instructions. It's even better than GNU-CC intrinsics, which is not a high bar. Another thing we're doing, we've got a prototype just about ready to publish where we're able to put invoke dynamic in the constant pool. And that means being able to assign a bootstrap method not to a call instruction, but to a point in the constant pool. And that means when you LDC it, a bootstrap method runs the first time you touch it. It fills in the constant, and then that constant is in your constant pool forever for you to use, and it can be of any type whatsoever. That's called constant dynamic, or Condi for short. Condi and India are a nice pair. And then finally we have something called bridge-o-matic or lazy bootstrap methods. The idea there is to be able to, once again, use a bootstrap method to tell what's in a method. So the first time you call the method, you run a bootstrap method for the method, and then that expands it. Why would you want to do that? That's crazy, isn't it? Well, no, actually, what about a two-string method? It has a ton of boilerplate in it. It's really stereotyped. You really want to have that sitting on disk in your application, especially if you never use it. Better if you can just, when you first use that toString method, spin it up real fast from some metadata, and then you have your code just as if it had been coded there all along, but you don't have to deal with it until then. So those are some of the ideas that we're working with in the near future. One other thing is not only are we putting invokedynamic in more places in the VM, we're putting it in more places in the source code. The idea there is we're working on some syntaxes. This is all TBD, but we think we've got a line on how to do it. To be able to actually, for the first time, write Java code that can create constant expressions which fold down to Indi and Condi. So you can write your own in Java. You don't have to spin bytecodes.
No ASM.
No ASM, yeah, no ASM. And so that will unlock creativity, I think, amongst more people than just those who spin bytecodes. So we'll find more uses for Indi and Condi.
Yep. I'm on the mic, yeah.
Yeah. Like my mic?
I'm going to explain a little bit about signature polymorphism for those who don't know, for the curious. So say we have a public class test. It has a method in it, m, takes some arguments, returns something. And we have a method m that's associated, looked up to that method, and we have a method handle that's looked up to that method as well. And if we look at this reflect method that invokes the Java lang reflect method m, we pass the arguments in, we pass the instance of test, we pass some values in here. And when we look at the handle method that calls the method handle, it looks almost the same. Looks very, very similar. But if you look at the comments here, the method signatures are actually different. If you look at in the source code and in the Java doc, you'll see that the method signature for Java lang reflect method takes an object and then a varargs object for all of the parameters. So it takes an object that's a receiver and all of the parameters, and the receiver could be null if it's static. And it's the instance test in this case because it's a virtual method. Whereas in the method handle version, it just takes a varargs and that's it. So you're wondering how the heck can that work? Is this going to be efficient? What are we going to do here? So if you look at the Java P bytecode, you can get some clues to what's going on with these special methods of a method handle invoke and invoke exact and the VarHandles methods, which are signature polymorphic. So I've deconstructed the bytecode here using Java P of the Java lang reflect method. And what you see going on, you see the invoke virtual at line 30 here, and you've got all this ceremony beforehand before you actually do the invoke virtual of the Java lang reflect invoke here with the method signature. See the object and the array of object here expressed as in bytecode method signature. And you've got essentially what I call packing the boxes. You have to create an array at the top here of size 3. It's in the green. And then the first argument has to be put into the array, the second argument, and the third argument. And you notice that the what are we calling 42 and 3.14 arguments, they have to be boxed into integer and double. So it's packing and boxing there. And that is quite a lot of bytecode, and it's quite hard for the VM to optimize this away using escape analysis and so forth like that. It's a really hard optimization problem. So signature polymorphism just does away with all that. And it says, here's Java C, whatever you see here as the types, just put them in as a signature instead. So in a sense, we have the loading of this. We just push A onto the stack, push the integer, push the double, and the signature is encoded into here directly rather than the varargs. And that is what signature polymorphism is. And then there's some nice sort of contract between this and the VM that understands what this means and how to optimize it under the covers. So it compresses it all down like so. And the C of signature polymorphism could be infinite in a sense, but actually in practice it's limited in terms of its arity. And also the types underneath the covers, we widen booleans, chars, shorts, and that to ints to reduce the sort of permutations we have under the covers to deal with all this. So hopefully that gives you a sense of what it is. And when you see this word, it's not so magic and strange. It's actually very simple in Java C what's actually going on, more complex in Hotspot. So now I'm going to talk about the concepts of lookup and invocation. So how do you actually get a method handle, say, to a method, a virtual method, to a field or something like this? You can consider method handles as a new and improved way to reflect over classes at runtime. There's an aesthetic judgment, you can decide on that or not, but we're trying to move people away from reflection to method handles as a way to operate on stuff. The difference between Java Lang reflection and here is access control occurs when you actually look up a method handle. It does all the work beforehand so that when you operate on the handle, you don't have to take that hit every time. And because of this, you have to guard these handles very carefully. If they're pointing to stuff that you don't want others to use, you have to guard these handles and make sure they don't leak out. So when you have these, keep them tight to you if they're important to you. Yeah, I don't think this diagram is doing anything useful, really, except that what we want to do is make setAccessible go away eventually. Every accessible object has a bit associated with it, whether it's accessible or not, and it conflates access control for fields with pounding on final fields as well, which we want to get rid of. Ultimately, we want to make final fields final so the JIT can actually optimize these things. But we're struggling to do it because setAccessible can stomp on final fields and turn them into non-final fields, which they did for good reasons in Java serialization, which we also want to change as well and try and fix that going forward. That's a separate problem. So there's some hard problems here before we may be able to get rid of this thing, but we're trying to actually get rid of it, encourage people to move away to Lookup. So I'm going to do some
Let me say something about Lookup first.
Yeah.
Lookup is a capability object. How many of you have used a lookup? Okay, small number. So setAccessible is a very crude hammer. You can take any pre-existing reflective thing and hammer it to make it crack the system open, and that means that it's hard to prove that any particular usage is correct. But with lookups, it's much more fine-grained. You take a lookup which represents your own capabilities, your own universe of allowed access actions, and that lookup can only give you method handles which correspond to things that you could have done with bytecode in the first place. So lookup lets you get to private fields, but it does not let you get to someone's private fields other than yourself. So it's much more graceful and it's easier to prove correct. And there are, of course, some sledgehammers hidden in the back closet where you can get to stuff that isn't your private. But it's very clear from code when you're doing that kind of a really edgy thing as opposed to the more pedestrian thing of getting to your own privates.
Hopefully we'll explain this a little bit more in some demos here. So if you know about this already, this is a JShell demo for you. So how would you do lookup method M just using Java Lang reflection? What you do is you get the class, you get the method, and then you would look at the method name like so, and then the parameter type like this. And if I get my my Vulkan def grip thing going in JShell, you can do this. So we have a method here. Then we just invoke, and we can do test t equals new test. Sorry, c new like so, and then we can invoke that. That should be familiar to everyone. Like so, that's very familiar to people using Java Lang reflection. So how will we do this using method handles? We essentially create a method handles.lookup here. Let's call it L. The context of this lookup is essentially the caller. So when you call lookup, it's caller sensitive, and it says, who am I? And it encapsulates who am I into the lookup. And that is where we can start doing our access control from who's looking up to whom and decide whether we're allowed to actually make this happen. So in this sense, you get a sense of how JShell's working here because it's creating anonymous inner classes here. In this sense, it would be different if you're doing this in the IDE, but we got a lookup with a lookup class. And once we got this lookup class, we can say find virtual like this and lookup M. So our reference class is C, our method is M, and then we have a method type that we need to create, which is our method signature. And a method type returns an int and takes an int. Let's see if that works. And we get a method handle out. And then we can essentially invoke it. So we can invoke it with exact semantics if we want to, which means that the method signature in the call site here has to match exactly the target. And that is a very efficient way of invoking. And if we don't get that right, we get to what's called a wrong method type exception. So this is where the sort of little bit of strangeness comes in here, that we have to actually do a cast like so. Oops. Oh gosh, yes, thank you. Like that. That cast is not encoded as an explicit cast with boxing and casting to an int. That actually says what is the return type of this signature polymorphic method, like so. Otherwise, you can just do the slow way with invoke, pass in C, and that will actually do transformations. It will do casting, it will do widening, primitive conversion, so forth, and that can be the slow path. Although there's some optimizations in there, it's not as optimal as you might think all the time. There are probably ways we could improve it in the future, but it's quite a hard thing to improve generally. So if you really want speed, use invoke exact rather than invoke there. So now let's look at the class C here. We have a private field in there. So can our shell, what we're doing in the shell, access that private field in there? So if we just do c.I equals 1, we can't do it because we got private access here. So what would we do? So if you're doing in reflection land, what you would do? Well, we would get declared field. What's that? It's the name. I think it's I. So we've got a field to private int C. So what happens if we try and set that with some value? We get an illegal access exception when we actually operate on it. So what happens if we try and look up to a field instead? Now, field is not a method, but the low-level mechanisms in method handles have bytecode equivalent functionality and behavior. So how would we look up a method handle to that? So we got our lookup L. We can find setter, like so forth. We need to specify a class, int.class. So are we allowed to look up that field from our context of where we're in?
I think you need to do L.in.
It shouldn't work. It won't work because we don't have access to it. So how do we get access to it? Because if we're in the same context, in this case we're in the same class loader, we're in the same module in a sense. So where you get around this, so what would we do if we're in the field? Let's go back to our field here. What we'd do, we would have to do setAccessible true, which is the blunt hammer here, and then we can do our set, and now we're all good. That is a bad way of doing it. We're trying to encourage people not to do it. I realize there's reasons why people need to do it, but we're trying to move people away. So what would we do instead? So we have something, MethodHandles .private lookup in, where we take our, let's have a look at the signature here. So we take our target class, which is c.class, and we take our lookup, we want to say teleport. Am I allowed to teleport into this thing? Do I have the right permissions to do so? Now we're actually allowed to do it. It gives us the permission to do it. So this is setAccessible, principled setAccessible on steroids. It won't stomp on final fields. It will just allow you to have accessibility. And we're actually using this in the JDK because some stuff in Java util concurrent wants to get access to fields in thread. And it's been using unsafe to do this. So we can use MethodHandles lookup private lookin to say, yes, I'm allowed to do this because I'm in the same boot class loader. And then I can use a method handle to access this rather than using unsafe. And the whole thing is much clearer on the contract between the thread and stripe 64 in this case. And we want to do it to more cases in Java util concurrent. Thread local random does the same thing as well. It's a much more principled way of doing it. I like the way it's turned out. So now we can invoke that Don't know why that's null. Why on earth is that null? Anyway, the demo.
Setters return null.
Pardon?
Setters return null.
Yes,
That's
of
their
course.
signature.
Yes, of course. What am I thinking?
They return void. Void appears as null to
Yes.
invoke.
I was thinking it was a VarHandle. So if we do 24 like this, so we got a getter instead when we get back what we set. Okay. Yeah, so it's kind of strange why null is returned because it's void. There's a signature polymorphism is popping its head out in an ugly way here.
If you didn't invoke exact, then it would come back as void.
Yep. So we can also do a find VarHandle on this class and do exactly the same thing with MethodHandle and then do compare and exchange and so forth like this on the field. So hopefully that's given you a flavor of that. How much time do we have left?
You're halfway through.
Okay. So let's continue on. So now there's MethodHandle combinators, which allow you to build up behavior in a sort of DSL-like manner. You'll see a lot of methods on MethodHandles that allow you to do some quite sophisticated stuff. And underneath the covers, the framework should actually optimize this and generate some quite efficient bytecode, which then the JIT can operate on. When you do this, you kind of need to think in reverse and think a bit like a compiler. So it's quite mind-bending if you're not used to this kind of thinking. Charlie Nutter has something called invokedynamic, which is a way of trying to do this in the right order and express this very cleanly. And maybe it's something we might want to consider going forward to make this easier to use. Basically, there's a bunch of methods to do argument and return value manipulation, and there's a bunch of stuff that do control flow, like if, else, try, catch, and loops. There's no switch yet. There's a bunch of things we could add here. I'll go show a quick demo. I'm not going to show all of it because we're running out of time. But I just want to get a quick, get the concept across. So I want to, I've created some snippets in here which are method handles to big integer add and big integer multiply. And I've just created some constants for myself. So the add dot type, you can see it takes two big integers and returns a big integer, nothing outstanding there. I want to combine these using method handle combinators, and I want to do something like this. I want to create a function like this. Now I'm using these combinators here. So the way to think about this is to actually have a different function x, y, comma, y prime. Like so, and then our function f of x is just a call to f prime x, comma, y. So this is thinking like a compiler might think, and you've got to think in like an AST manner as well. So once you get this style of thinking coming in and manipulating arguments on the stack, then it becomes much easier to understand how combinators work. So how we do this? So we have method handles dot collect arguments here. And what we want to do is we want to say, well, our last thing in the tree here is a multiply operation. So we got a mul method here. And then we want to combine the arguments we take from add at position 0 in our argument list and return a value and pass that to mul as the first value, and the other mul can take the third value in this list. That makes sense. So let's just look at the method handle here. Function option f1, f prime. So we get a method handle here. It takes three values. So this is my f prime function here. It takes x, y, and y prime. So we can actually invoke this. 1, 2, 2. Oh, it's nothing exciting. We get the right value out here. Now we want to sort of up-level that again. So we want to pass in only two arguments. So what do we do there? We have method handles dot permute arguments. So we want to take f prime as input here. We want the method type of just taking two big integers and returning a big integer. And it's basically saying we've got three arguments here. It's the first one and the second one and the second one, or the 0th argument and the first and that. So we get a method handle here, string 34. and we see it just takes a big integer. Big integer, if we invoke here 1, 2, we get the same value. So this is how you have to think in this model, and it gets a little bit more complicated. Say we want to look up combinators to loops, which we recently, Michael Hupt added. I don't have time to go into this, but this is a way that you might do a MethodHandle combinator to sum up big integers in a loop. Essentially, we have a counted loop. Here, it takes how many things do we need to count. It's going to accept a big integer array as input into this MethodHandle, but it needs to know how many things to count. So it's the array length of what you pass in as a big integer array. And then we need to say, what's our initial loop value, loop result value? It's going to be 0. And then we need a way to actually sum up the values. So this is the way I'm doing it here. And we need to shuffle our arguments a bit like we did before to get things in the right place so we can extract an element out of the array and sum it up to our loop value and swap arguments, so forth like that. So I don't have time to explain that, but that's how you do it. It gets complicated a little more where you think about this. But it's hopefully the end result here is you'll get efficient bytecode out, and then the JIT can efficiently operate on it. So this is not something you would do normally in source code. This is something you might do in an INDI when you're dynamically generating stuff, so you don't have to use ASM and stuff like this.
If you stick native method handles that punch down to single instructions instead of the big integer primitives that he's using, then this loop stuff combines them in the right way, so you actually do get your vector loop that fits in one cache line at the end.
And in fact, this is the same tricks that we've been doing with Vector API. Ian Graves in Intel, and he's been doing these loops and doing the code snippets thing and getting very efficient loops with AVX instructions and vectorized loops in there, and it actually pops out amazingly what the hotspot can do and just crunch it all down to a very, very tight loop. Okay, so that's MethodHandle combinators. So quick thing about constant dynamic to explain this. So this is something done by Lois, what's this? Fulton. It's something internal, but I think is going to come out as a patch or as in some branch that you can have a look at. So the idea is to invoke dynamic for call sites, to do it for constant pool. There's only a limited way you can express constants in the constant pool, primitives, class, method type, method handle. What happens if I wanted to have VarHandle in the constant pool? I can't do it today. I wanted to, but it was just too much work to do it and questionable whether we should add another explicit type to the constant pool. Is there a way we can make this almost the last thing we add in terms of expressing stuff in the constant pool? It's another level, this little classic level of indirection trick, essentially. So it's an experimental mechanism. The idea is you should be able to LDC, that's a bytecode for loading a constant, LDC almost anything. And the VM appeals to a bootstrap method to say, what the heck are you going to return to me, essentially, from some constant arguments? Like Indy has a bunch of constant arguments you pass to it. Constant dynamic has a bunch of constant arguments. And effectively, these are like lazy static finals. And this is interesting to us inside the JDK because we have circularity issues. I'm wondering if we can use this to break the circularity chain or the cycle, if you were, so that when you need something, you don't have to put it in a static initializer. It's initialized when you actually need it, not up front when you do class initialization. So here's an example. This is how you'd write an efficient VarHandle mechanism today. You would have a static final. You would initialize it in a static initializer, and then you'd use it later on, say like compare and set in a method like this. This is ugly. Dougley hates this. It's no worse than atomic field updater. Dougley hates atomic field updater too, so it doesn't improve matters. Yeah. Yep, it's where we are. But I want this. I really do want to get to kind of this type of thing, or this type of expression. We're using the same syntax we use for method references here. Now, there are issues here in terms of source code and overriding methods and all this, but that's the expression I want to sort of get to, or something close to it. We express what we want to the field, and we have a VarHandle to it, but we want that efficiency. We want this to be rooted as a static final. We want it to be rooted as a constant, so the hotspot can constant fold all the access when we do this compare and set operation. So here's, I've been playing around with the prototype, and I did some hacking and got some Java P output here when we encode this. So here's an example of this cas method I showed. So here at line 0, we have the LDC instead of referring to a static final field here. We say load this constant. What is this constant? Well, in the constant pool at 23, it points to something at 0, which is our bootstrap method, which says an invoke static to something here, which says get me the VarHandle for this information with the static constants here of foo, s, and Java lang string. So it has all the means to do this, like in the static initializer, but it's lazy, and it invokes this, an appeal to Java to go up and do this, rather than its static initialization. So that's the essence of it, and it's going to be recursive too, because we have no way of representing int.class in the constant pool. If you compile, if you refer to int.class in Java source code and compile it, you might be surprised about how Java-C encodes that information. So if this field was an int instead of a Java lang string, we might appeal to another condi coming in to actually resolve what that means. And you can actually take this even further and get lazy AST trees, or trees lazily sort of produced. We think we can push this quite hard.
That's the reason we don't just simulate it with a null-array indie, because if we just wanted to get a one-off LDC of something, then a null-array indie works pretty well. But if you want to have constants referring to constants, basically upgrade the whole constant pool, not just the parts that the LDC touches, then you need this.
Yep. This feeds off indie as well. Indie has a certain restricted way to represent constants, but we can make indie even more powerful with this mechanism as well. Okay. Start ramping up.
All right. So this is all speculative. Well, you already did the safe harbor statement. But there's some future combinators. We haven't come to the end of we haven't come to the last combinator you will ever need. And so for starters, the switch statement is something you can write in Java, and it has a bytecode for it. But you can't write that in MethodHandles, and there are actually good reasons to fix it, other than just sort of picking a thread off your sweater. A switch combinator for MethodHandles might be unlike a regular switch in that it might be open-ended. You might actually have the switch itself have a little bootstrap method in the default that says every time you see a new switch selector, do a little logic to say, well, should this have a specialized case statement for it? And so you develop the cases lazily. That's a very powerful technique that's used, for example, in the PyPy interpreter to have the language runtime sort of grow itself as the user exercises new paths. So you don't have to compile it all up front. You just have the thing compile itself as needed. Another one that's really simple is synchronize on object. We don't have a way to do that. That's built into the language. There's a number of really simple bytecodes like monitor enter, monitor exit, I add, L mul, compare bytecodes. Those are all bytecodes which have a really simple, I want to say, stereotyped or monomorphic job. We should have built-in method handles for all those in some place that so you can get to it. Right now, the workaround is you code a method of your own that does the synchronization or the add or whatever, and then you pick it up. That's the secret reason why Paul's demo earlier used big integers instead of plain longs or something, because there aren't any well-known method handles for getting at long add or float add. It's just an oversight that we'll eventually fill in. A much deeper one would be partial construction. This is the very small number of people have said, why don't you give me invoke special init in my superclass, because I want to get my super constructor call while I'm in the middle of initializing an object. Groovy wants this, for example. This is really hard to do because it disturbs the most complicated part of the verifier, which is the part that makes sure that you initialize the super part of yourself in your constructor before your constructor initializes the rest of the object. It involves partial object states, which are very dangerous, very insecure. If we were to give people hooks to just play around with partial objects, then we could, I don't know, someone might build a deserialization framework out of it or something, and then there'd be all sorts of security problems. Oh, wait, yeah. So, We think there's ways to do this using the MethodHandle framework, but it's kind of a research problem still. The idea would be to have your partially constructed object in a kind of a locked box that only authorized combinators could get into, and so you work on the object sort of at a distance while it's in the uninitialized form, but the locked box ensures that you apply the right sequence of constructor components in it. That way you can prove that nobody does anything that they couldn't already do in bytecode, and nobody does anything in the wrong order that the verifier would reject, and yet it's all done with MethodHandles. So we think we have a line on eventually filling in that hole, and that will be maybe the last thing that you can do today in bytecode that you can't do with MethodHandles. Higher level things, sort of Dynalink level things. Multi-methods are interesting. What if you had a MethodHandle combinator that said, I know I'm going to call a whole family of different methods, but depending on the arguments, I want to look at the argument and then decide which of the family I'm going to call, right? We make stuff like this, right? We make like virtual object hierarchies that have this flavor, and a multi-method can potentially dispatch on all the arguments instead of just the receiver argument. Some languages do this. Sometimes it's useful. The key thing is that you run different snippets of code depending on the dynamic value of one or more arguments. This is the kind of thing you can capture in a combinator, and I think we might come up with something like that in the future as a utility. Lest you think this is too weird and researchy, a simple example of a multi-method that fits the definition I just slipped by you would be printf. Printf looks at the dynamic value of its first argument, which is a format string, and uses that to count and interpret the remaining arguments, right? So imagine a printf that sort of for every format string or every class of format strings went to a different optimized method. You might be able to get printf that doesn't have so much interpretive overhead in it. And then, of course, if you constant fold the format string, then the multi-method collapses to a single method, but the code is actually optimized for that one particular format string. So that's an example of multi-methods. Well, actually, you use them every day, and they could be optimized better. Also, control flow that's slightly non-local. Do break is something we write. Sometimes have you written a do statement in Java where you don't intend to do it more than once because you want to break out of it and you break to a label? That's a combinator too. And so that's like a piece of language capability that's missing from MethodHandles. You can build it yourself, of course, but it'd be nice to have it built in so you know the system's going to optimize it. What do we got? We got 5 minutes. Okay, I'm going to race through this. Do you have any more? Okay. All right. I've got the podium. I'm going to talk about this a little bit in the next talk too, but basically one of the things we want to do is put bootstrap methods in more places. So Indy and Condi have already been talked about. I mentioned the lazy boilerplate method earlier. There are other things we might want to be able to do, such as what if you could have a superclass which said, every one of my subclasses will have a toString method. If they don't define the toString method, then I'm going to define it for them as a piece of boilerplate that expands differently in each subclass. Right? That's not a bad idea, and we can do that with a bootstrap method and proper wiring in the VM. And also we want to be able to do bootstrap methods not only at the time we do them now, which is on first execution, but also maybe a little bit more eagerly when the class is linked, or maybe even super early at AOT time. This is something that we have to do in some cases now, and we want to generalize this pattern of being able to sort of pre-vision or provision the action of a bootstrap method at AOT time, because AOT is becoming a reality in the Java world. There have been AOT compilers for a long time now. We have an AOT compiler in Java 9, and let's teach that AOT compiler to do some interesting partial bootstrapping at AOT time. This will give us Java applications that are quicker to start up. I want to say a couple words about code formats. Since this is an invocation, when you invocation talk, when you invoke some piece of code. It doesn't have to be bytecodes. It could be MethodHandles and combinators. And we're aiming to have a close symmetry and synergy between what you can do in bytecodes and what you can do in MethodHandles. But then maybe also we want a third thing someday, what I call transparent expressions. This would be expressions which are like bytecodes, easy to assemble sequentially. but they're less contextual. It's just basically a sequence of tokens. They're not as compact as bytecodes, but they're easier to understand than bytecodes. You basically would say, here's in a method handle, oh, that means execute that method handle on whatever's on the stack, and then push the result of the method handle. And so you write code that looks like forth code. The advantage of these is it would be easy to analyze these backwards without executing them. You'd be able to say, oh yeah, I see someone has asked me to do an as type transform on a method handle. I'm going to make a conclusion about that that doesn't necessarily involve executing it. We talked about constant formats, so I'll just quit that, except there's a few extra things we want to do. Condi isn't actually the last. We also want a grouping construct so we can have more than 2 to the 16 constants. And that's not too hard to do, but we haven't figured it out yet. We want to do new kinds of calling sequences. Right now, we have the native calling sequence, which is strongly typed by the verifier, but we have also method handle-based calling sequences. We have the reflective one, which Paul already showed you with all the boxing. But then there's some other possibilities, too. We think we want a way to wrap up a sequence of strongly typed arguments without boxing, but in one sort of shrink-wrapped slug of data on the stack, not necessarily an object. This is where value types come in. And then be able to efficiently hold that until it's time to call a method handle, then put them together and not have any boxing, just basically slide the argument list into place. Arguments should be worked backwards too. This is object deconstruction. If you take a bunch of arguments and you construct an object, you should be able to reverse that process too, take the object apart. This gives us a handle on doing, let's say, deserialization and serialization done right. You know, you want this, you want a strongly typed set of operations that does the expand and contract.
And efficient pattern matching as well.
Yes, and it gives you pattern matching. And a final call out to coroutines. We're not ready to say much about that yet, but basically that's where you start invoking slices of methods that haven't finished, but you're going to help them finish by invoking the part that isn't done yet. Paul, we're done. These are some more links to more information. Watch the OpenJDK traffic. We're thinking about all this stuff.
I think we have about 3 minutes for questions. Everyone's stunned. Okay.
We're working on one, yeah. Mm-hmm. To come out soon.
Yeah.
There's a bug RFE, a bug track RFE that talks in detail about it, which we should probably mention.
Mm. Okay. Thank you.
Thank you.